So now we're up to a part where we're thinking about actually doing some calculations, and physics is fabulous because you can actually calculate how long is this pen going to spend in the air if I throw it with a certain speed, or how far is a car going to travel if it moves along in a certain way. So we're going to kind of put some equations to use now, but in a way that is consistent, you can use in every kind of problem that you come across, so that you have a way to start when you tackle a problem. A lot of times people say, well, I understand how to do it, I understand everything about this, but I just never know how to start. So that's what we're going to do with this, is we're going to look at doing kinematics calculations. Kinematics is the study of motion, and find a way that's consistent that you can use over and over again, even if it looks like a problem that's completely different. All right, so before we get started, I just want to point out there are two equations that we have seen before. The equation tells us that the average velocity is the displacement divided by the time. That's kind of how these triangles worked. The thing we cared about, the average velocity, is displacement divided by time. And this one is the acceleration formula, that the acceleration is the change in velocity, v2 minus v1, divided by the time. And again, we can use these equations to find anything we want. If we want to find the displacement is the average velocity times time. Or if we wanted to find the change in velocity and we knew the accelerations, we could cover it up and see the change in velocity is actually the acceleration times the time, because they're next to each other. We'll do more of that as we go along. So in this problem we have, and I always start with this one, it seems really simple, and some people have done physics before. They'll say, well, I know how to answer this just by reading it, right? I can just look at it and I know the answer. Well, perhaps that's true, but this approach that we're going to build up right now, you can use for problems that are much more complicated, and we'll do some pretty soon. Okay, so really bear with me and kind of think about the process, because that's really what's important for physics. So we're told we have a car that's moving to the right with constant speed, and we're told that the speed is 40 meters per second. So every second it covers 40 meters, and then the next second it goes another 40 meters, the next second it covers another 40 meters. And we're told it travels like that for 6 seconds, and we want to find out how far it travels in that time. Well, the way to answer these kinds of problems is always to show the object at the start, and tell yourself 3 things at each point you want to know. What's the time, what's the position, and what's the speed? So the time is, this is the start of the problem, starting here, and it's going to go over to this side. And we know that by the time it gets to the end of the problem, that's at time t equals 6 seconds. At the beginning, well, it doesn't say where it is, but I'm going to call this position number 1. Let's call it 0, right? We can, in any of these problems, we can pretty much say that it starts at 0. And where does it get to at the end? Well, how far does it travel? We're trying to find out where it got to. We don't know this. So we don't know what x2 is. And what you're going to find as we do these problems is that it'll be clear the thing we don't know and the things we do know, and it'll help us to find out how to tackle the problem. Okay, what about the velocity at the start? The problem says, moves to the right. So this speed of 40 meters per second is the speed that it had at the start. It didn't say that it started at rest or it had some different speed. We're told that it travels at this speed constantly. So that's what it started with. That's also its final speed, 40 meters per second. All right. Now, at this stage, it's always useful to kind of draw something we spent time on, which is the motion diagram, just to put a motion diagram on top of this. So this car, I know whatever speed it's traveling at, 40 meters per second, it's going at a constant speed to the right, and I know what that looks like. So this takes me 12 seconds to quickly draw up a motion diagram, and looking at this, I know there's no change in the velocity, so I know the acceleration is 0. But I put that on there just to remind me that as this car is traveling from here to here, I can look at a glance at this and understand how it's behaving. So we're trying to find out what is this distance from here to here, delta x. We don't know what this distance is, and this, if we found x2, it's the same thing. So now I can look at this picture. I don't have to go back and read the problem again. One of the things that people get stuck on is that they go back to the problem, they reread it and reread it and reread it. And what it really means is that you haven't put it into a format that your brain is able to really kind of digest, the picture is supposed to be something that makes it easy for you to see what's happening. So I can see here that at the start, where it's at the beginning of the road, it's traveling at this speed. At the end, it still has the same speed. 6 seconds later, and I'm trying to find where it got to. Okay, so now we take a breath. All the hard work is actually in this picture. Now we go back to the equations that we have. We're trying to find how far the car goes. And that's really delta x. Well, here's delta x. So I can use that formula that relates delta x to the average velocity and time. I can see that delta x is the average velocity times the time. Okay? Then you have to say to yourself, well, what's the average velocity? Well, an average of anything is always, when we've got these kinds of simple problems, let's say you had 2 bundles of money, and what was the average amount of money? If you wanted to split it evenly between 2 people, what you do, you put it all together, you add it all up, and then you split it in half. And so that's always going to be true for us, is that the average velocity is always going to equal 1/2 of v1 plus v2 in all of our problems. We've got constant accelerations or no accelerations, and so we can always take this as being true. Well, in this problem, you say, well, what's v1? Well, I know v1 is 40. And what's v2? Well, v2 is also 40. So 1/2 of 80 is 40 meters per second. And they say, well, of course I knew that, right? It was constant speed. If something's got constant speed, the average is just the same value. But the reason I'm doing this in all its kind of gory details here is that if the car was not traveling at a constant speed, we could still use the same technique. The average velocity will be 1/2 of the starting velocity plus the final velocity. All right, and this is also a good point to kind of remember, is that you should always check as you do any calculation to see if it makes sense. The average velocity should be exactly the same as the velocity at any point along the way here, because the speed is constant. So we did do the math right. All right, so now we can plug it back in. So we know that the displacement, or the change in position, is the average velocity 40 meters per second times the time, which was 6 seconds. Now, most of the time I don't put in the units for this class. As long as you know that you always start out with meters per second and seconds and meters and the right units, the same units, then you can actually ignore the units. But this one time I'm going to show it, because you can see the seconds are on the top here, seconds are down below there, we can forget about them. Always just multiply the numbers first, right? Forget about the units to begin with. So 6 times 40 is 240. And the distance that we have left, the units, are meters. So this says that this car, after undergoing this kind of motion for 6 seconds, will have traveled 240 meters. Well, we think back and it seems okay, because every second it was traveling 40, a distance of 40 meters. So it went 40 plus another 40 plus another 40, that's 120, plus another 40 plus another 40, that's 200, plus another 40, that's 240. And so we could actually just keep on adding them up to get this speed if we want, or this distance. But the formula helps us get it much more quickly, especially if the problem had said it traveled at this speed for 762 seconds. You don't want to have to add 40 plus 40 plus 40 that many times. All right, so this is the format that's going to work for any of our problems. When you draw out the picture, at the start show the time, position, and speed. At the end show the time, position, and speed. The thing that you don't know, you can just circle. Identify the things that you don't know. If you look at the motion diagram, that kind of gives you an overall sense of how the thing's traveling. Make sure that's consistent with the way you're thinking about the problem. And then pick from the equations that we have here, which are the ones that's going to help you find what you want. If you wanted to find the acceleration, then this is the one that you would use. And I guess the other thing I should just point out is that we do have one more equation that's going to help us. Right? It's this one. Is that the average is always 1/2 of v1 plus v2. So given these two and this one, you can solve any of the problems that we encounter. Some people have done physics before and might say, oh, there are 4 kinematics equations. Well, there's really only 2 that you need. The other 2 come from those first 2. It does make some problems easier if you want to memorize 4 different formulas. So I don't care how you tackle it, but I can guarantee that every problem that we do, as long as you use these 2 equations and think about the average this way, you'll be set.